Welcome to the fourth lesson in Session 3 on solving systems of equations algebraically. When solving systems of equations algebraically, there are two methods we're going to be using. First is substitution, and the second is elimination. Both of these methods are used to eliminate one of the two variables so that the other variable can be solved for algebraically. Once we've solved for the first variable, then we're going to use substitution, plug it back into one of the original equations to identify the value of the second variable. First, we're going to start with the substitution method. The substitution method is most convenient when one of the two equations has an isolated variable, but can also be used when this is not the case. So in our example, we have y equals the quantity of x plus 1, and the second equation is 2x plus y equals 10. So notice in the first equation, the variable y is already isolated. This is a perfect example when substitution is a convenient method for solving the system. Since we've already identified the value of y in terms of an expression equal to x plus 1, I can then substitute the quantity of x plus 1 in place of y in the second equation. Doing so gives us 2x plus the quantity of x plus 1 equals 10. Now that we've produced a single equation using a single variable, I can use my algebra skills to isolate the variable and identify the value for x. Combining like terms gives us 3x plus 1 equals 9, and then using good equation skills, we isolate the variable x and get the value of 3. Once I've solved for the variable x, now I'm going to use substitution, plug it back into the first equation in this case, y equals x plus 1. Since I know the value of x, I can then plug that in, and we get y equals 3 plus 1, which gives us a value of 4. Always express our answer of a system in terms of in an ordered pair. So the solution is going to be expressed as 3, 4. Next, we're going to learn the elimination method. The elimination method is preferable when both of the equations are given to us in standard form. So for example, 2x plus 4y equals 12 and 6x minus 4y equals 4. Notice how the terms that contain x are lined up, the terms that contain y are lined up, and on the opposite side of the equation, the constants are lined up. This is a perfect example of when we want to use elimination. So now, paying close attention to the variables, the coefficients of y, we have a positive 4 and a negative 4. This is helpful because they are opposites of each other. So when we add the two equations together, the terms that contain y are going to cancel each other out. So doing so, we have 2x plus 6x gives us 8x, 4y and negative 4y cancel out, and on the right side we have 12 plus 4, which gives us 16. So what we end up with is a nice simple one-step equation, 8x equals 16. Dividing 8 by both sides of this result gives us a value of x equal to 2. Once we've identified the first variable, we're now going to plug that value back into one of the two equations. It doesn't matter which one. Their solution is going to be the same either way. So in this case, we'll go ahead and select the first equation. So 2x plus 4y equals 12. We know the value of x is equal to 2. So when we substitute that value of 2 back into the first equation, we end up with 2 times 2 plus 4y equals 12. And now we simplify and solve the equation, and we end up with a value of y equal to 2. Expressing our answer as an ordered pair gives us our solution of 2, 2. Now, it's nice when the coefficients are opposites, but that's not always going to be the case. So in the next example, we're going to show you how sometimes we have to manipulate the system using multiplication in order to produce opposite coefficients. Sometimes we can get by with multiplying one equation. Sometimes we'll have to multiply both equations. So in our next example, we've got 2x plus 3y equals 0, and we have x minus 4y equals negative 11. So notice if I add these two equations together as they're presented, neither of the variables are going to eliminate themselves. 2x and x is 3x. 3x minus 4y is negative 1y. So we have to multiply one or both of the equations in order to produce the opposite coefficients. So the easiest way to do it in this case is to multiply the second equation by negative 2. So notice the first equation stays exactly the same, 2x plus 3y equals 0, while the second equation gets multiplied by negative 2, producing negative 2x plus 8y equal to positive 22. Now I've produced opposite coefficients for the term x with positive 2 and negative 2. Now I'm in a position where I can add the two equations together and eliminate the variable x. Doing so gives us 11y equal to 22, allowing us to find the value of y equal to 2. Now we're not done. We still have to go plug that back into one of the two equations and solve for x. So y is equal to 2. Plugging that back into the second equation, we get x minus 4 times 2 is equal to negative 11. Simplifying and solving gives us a value of x equal to negative 3. Expressing our answer, we have negative 3, 2 as our solution. Now, when we solved systems of equations by graphing, we sometimes had cases where we had no solution and infinite solution. And visually, we were able to identify a no solution when a system had no solution by looking at parallel lines that never intersected. So that system would have no solution. When a system had infinite solutions, we produced coincident lines, two lines that were right on top of each other. Now, when solving algebraically, we're not going to have the visual representation, but we still need to identify when a system has no solution and when a system has infinite solutions. So when solving systems, there are times when both of the variables get canceled out. When this occurs, we need to analyze the result and determine if the system has no solution or infinite solutions. So when both variables cancel out, and this can occur through substitution or elimination, where x and y will eliminate, we know our solution is either going to be no solution or infinite solutions. Now, if the result is true after the variables cancel out, then that tells us the system has an infinite number of solutions. If the result is false, when both of the variables cancel out, then there is not a combination of variables that will satisfy the system, and we have no solution. So in these two examples, the first one, example 3, we have 2x minus 3y equals 12, and negative 2x plus 3y equals negative 12. Now notice both variables have opposite coefficients. So using elimination here, we see when we add the two equations together, the 2x and the negative 2x cancel out, the negative 3y and the positive 3y cancel out, giving us 0 on the left side, and the 12 and the negative 12 cancel out, giving us 0 on the right side. So when both variables cancel out, we need to analyze the result. So what we have left is 0 equal to 0. This is a true statement. So whenever the variables cancel out and we're left with a true statement, our answer is going to be infinite solutions. On the right, we have a case where we're going to use substitution. X is isolated, and we know x is equal to negative 3y plus 1. So we're going to substitute negative 3y plus 1 in for x in the first equation, giving us 2 times the quantity of negative 3y plus 1 plus 6y equal to 4. Distributing gives us negative 6y minus 2 plus 6y equals 4. Notice they have negative 6y and positive 6y on the same side of the equation, so when we combine like terms, those two terms containing y will cancel out. Again, we have a case where the x is canceled out and the y is canceled out, and what we have left is negative 2 equal to 4. Now, negative 2 does not equal to 4, so when both variables cancel out, in this case, we have a false statement. So when a false statement is produced, our answer is no solution. So that wraps up the lesson. Please, in order to receive credit for completing the lesson, you must successfully complete the quiz. Good luck.